And hello there. This video is on the question I left in the classroom at the end today. So in particular, I will talk about how to deal with problems that has initial conditions given not at t equals to 0. So let's take a look at that. So today in the class we had this example that is a second order constant coefficient equation with initial data given at t equals to 0. Here notice there's 0, and we found the two roots and we wrote out the general solution form, and then we put in the initial condition and find out C1 and C2, and then we plug it in, and that is the solution. And this is what we did towards the end of the class today. Now, the question now is, if I make a little change. Okay, now this equation is the same, but now we have different initial condition. Initial condition takes the same value, but now is assigned at a different time. So at t equals to 2 are they given. So how do you solve this? Well, one way will be, we'll just plug in the general solution, its standard form, like that, and then we differentiate, and then we plug in the initial conditions, and we solve for C1 and C2, and expect some tough computations along the way, and we'll deal with it, and we'll figure that out, which will work, but probably a smarter way will be using a different form of general solution. So the trick here is to switch t with t minus t naught, where t naught is the time t where initial value is assigned. Here will be t minus 2. So if we do that and we take this form and switch t into t minus 2 and t minus 2, and look, this is the one we get. So here's t minus 2, here's t minus 2. And you can differentiate this once. Just the product rule, okay? Differentiate this one in t, you get a C2, and multiply by the exponential function, this one, and then you keep the first term here, and then differentiate the exponential function, which gives you a negative 1. Okay, and now you can plug in the initial condition, so, and y at 2. Now you see, with this expression, when you set in t equals to 2, that's 0, and that's 0. Alright? So that will be 0, and 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 that will be 0. So it's very simple. So when you put y t equals to 0, here you just get C1. So C1 equals to 2. And you put in 0 here, what would you get? You get C2 minus C1. That's all you have, right? And that shall be 1. And you quickly solve for C1 and C2, and that's what you get. And then you plug back in and write out the general solution, okay? Be careful. You have to keep t minus 2 here, and you have to keep t minus 2 here. Well, let's think a little bit. What are we actually doing? You see, during this process, t minus 2 always appears together instead of t. So it's t minus 2 all the way along. So it's like we are thinking the time variable now is t minus 2 instead of t, right? So why does it work? And for what kind of a equation will such a trick work? So let's take a look, be a bit more abstract. So we make an observation that the equation now is autonomous. Remember this concept? We say an equation is autonomous if the time variable t does not appear in the equation. So this equation is constant coefficient, right? So there's no t in it. So what does that mean? Well, that means basically how the solution changes, how it evolves in time, only depends on the value of the solution, not on the particular time when it's happening. So in that case, we could introduce a new time variable. Let's call it tau, and set it to be t minus t naught. T naught is where the initial value is assigned. So here will be t minus 2. And since tau is nothing but t minus a constant, so you can think this is a time variable. You kind of shift the time 2 units into the future. Okay, and then indeed tau will equal to dt, and then as an independent variable, if you differentiate in tau or differentiate in t, it's the same, right? So now thinking y as a function of tau, not t, the derivatives will not change. It will remain the same, and we will get the same differential equation. The equation remains the same. And now let's look at the initial condition. Now, y for tau, so when t equals to 2, what does tau equal to? Well, tau equals to 0, right? So now we have an initial condition given at tau equals to 0. So this whole problem here becomes the same problem as the one we started with, where the initial conditions are given at tau equals to 0. The difference is now we call the time variable tau. So you can copy down that solution. Wherever you have t, you have to write its tau, right? So that's the solution. You're thinking tau as the independent variable. And then you can plug back in what is tau. Tau is nothing but t minus 2. So plug it in, t minus 2 for tau, and t minus 2 for tau, and this is your solution. And of course, it's the same as the kind of the second method we just talked about now. Okay, so hope this is helpful. If you have any questions, always ask me. Okay, bye.